Today on Macaulay Math, we're doing trig of any angle. Intro. Okay, good day. I'm Professor Macaulay. This is Math 150 Pre-Calculus, Lesson 19 on trigonometry of any angle. Our goals for today. We're going to evaluate trigonometric functions of any angle. We're going to use reference angles to evaluate trigonometric functions, and we're going to evaluate trigonometric functions of real numbers. In this lesson, we expand the use of the unit circle, which was discussed in the previous lesson. Since the trigonometric functions are periodic, solutions to trigonometric functions are repeated. Using reference angles, the unit circle can be used to solve any angle that is a multiple of an angle that is on the unit circle. Let's get started.
So, trigonometry of any angle. And when we're talking about trigonometry of any angle, you can think of any angle that is placed in the standard position, and it does not have to be on the unit circle. We can have some value r. Now, in all of these instances, if I open an angle theta to some point xy, this ray r goes from the origin to the point xy. Then r is just the distance from the origin to that point xy. And you can see that right here. This is just the Pythagorean theorem solving for a little c. You got a squared plus b squared is equal to c squared. And if I take the square root of both sides, I would get this r in the c position. And in every case, you can kind of think of this going back to your old SOHCAHTOA. This r is just the hypotenuse of some right triangle. And so when I say the sine of theta, I am talking the opposite side, which in every instance is going to be the y value, over r, which is going to be that distance from theta to the point, and in every case that'll be the hypotenuse of a right angle. So sine theta will be y over r, the cosine of theta x over r, the tangent of theta y over x, and then cosecant, secant, and cotangent will be just the reciprocals of their corresponding trig expression. Second, reference angles. Let theta be an angle in the standard position. So theta can be any angle. Its reference angle is the acute angle theta prime formed by the terminal side of theta and the horizontal axis. So the terminal side, let's go back to this picture here. This is your initial ray, and this here is your terminal ray. So when I talk about the terminal side, we're talking about that terminal ray, and then the horizontal axis, that is your x-axis. So what does that look like? So as a quick example here, it says if theta is 3 pi over 4, find the reference angle theta prime. So I put 3 pi over 4 here in the standard position. Here is my initial ray, here is my terminal ray. And so theta prime will be the acute angle. So acute, remember, between 0 and 90 degrees, or between 0 and 2 pi radians. Acute angle is going to be this angle right here. So this angle right here is my theta prime. There is my horizontal axis. Here is the terminal ray. This is an acute angle. Now, depending on where theta lies, for every quadrant that theta could be in, this is going to be a little bit different. But if you think about it, I have 3 pi over 4. If I go all the way to here, in this case, an angle in the second quadrant, from the starting point here all the way around half a circle, that is 1 pi radians. So 3 pi over 4 plus theta prime in this case has to equal pi. So 3 pi over 4 plus theta prime has to equal pi units. So I will subtract 3 pi over 4 from both sides. That'll leave me theta prime is equal to, now I've got this pi. How many fourths are in 1 pi? Well, there are 4 4/4 times pi in 1 pi. 4/4 makes 1. 1 times pi is just pi. And I'm subtracting away the 3 pi over 4. 4 minus 3 is pi over 4 radians. All right, moving on. I do have the unit circle on here for me to refer back to when we get to it. Again, please, please, please commit this thing to your long-term memory. Example, determine the exact value of the 6 trigonometric functions of the angle theta. Now, in this case, my angle theta starts here and goes all the way around to here. So this is my theta. All right, so it says determine the exact value of the 6 trigonometric functions of the angle theta. So all I am doing here is I am using what we had on this first slide. I'm going to go, my sine of theta is y over r, my cosine of theta is x over r, and go through all of those. But when I look at this, I already know what my x value is, I know what my y value is, but I don't know what my r value is. So I'm going to do a simple Pythagorean theorem, a simple distance formula, to figure out what r is. And in this case, r is going to equal to the square root of 12 squared plus negative 5 squared. And again, I can't stress this enough. If you're using a calculator to make this calculation, make sure that you put that negative 5 in parentheses. So I get r is equal to the square root. 12 squared is 144. 5 squared is 25. I get r equaling the square root of 169. And I know that r is just 13. This is one of those Pythagorean triples. We did it in the last lesson. You got your 5, 12, and 13. So they want me to find the exact value of the 6 trigonometric functions. We will put those up. We've been doing problems like this for a couple days now. I have the sine of theta. I have the cosine of theta. I have the tangent of theta. I have the cosecant of theta. I have the secant of theta. And I have the cotangent of theta. All right, so since r is 13, I can say that the sine is the y value over r. And again, I'm just getting them from this table that we had at the beginning. So y over r would be negative 5 over 13. Cosine is x over r, so 12 over 13. And tangent is y over x, so negative 5 over 12. And then the cosecant, secant, and cotangent will just be the reciprocals of these 3 values. So negative 5 over 13 becomes negative 13 over 5. The reciprocal of 12 over 13 is 13 over 12. And the reciprocal of negative 5 over 12 is negative 12 over 5. All right, next problem. It says state the quadrant in which theta lies. Now here, they say that the secant of theta is greater than 0. That implies that it is positive. And here they say that the cotangent of theta is less than 0. That implies that it is negative. All right, so if we remember that the secant of theta is equal to 1 over the cosine of theta. Cosine of theta is only positive where the x values are positive. So if I come over here to visualize this, secant of theta can only be positive in these 2 quadrants. So I'm just going to grab another color here, say red, and say that the secant of theta is positive in these 2 quadrants. All right. Now, when cotangent is negative, now remember that the cotangent of theta is equal to the cosine of theta over the sine of theta, and we need that to be negative. Now, the only time that cotangent of theta can be negative is if either the sine or the cosine is positive, and then the other value is negative. So for cotangent to be negative, if cosine is positive, sine has to be negative. If the cosine is negative, then the sine has to be positive. Now there's only 2 quadrants where that is true. In the second quadrant, cosine is negative, but the sine is positive. In the fourth quadrant, the cosine is positive, but the sine is negative. So the only place where both the secant of theta is greater than 0 and the cotangent of theta is less than 0 is in the fourth quadrant. Next, it says find the reference angle for the given special angle. So here's my first angle theta at 315 degrees. So if I draw that in, I'm starting here and going up to there. And this is my theta equals 315 degrees. Its reference angle is therefore this angle right there. It is the acute angle from the terminal side and the horizontal axis. So 315 is almost the 360 degrees. In fact, that's how I'm going to get my theta prime is, in this case, the closest distance to the horizontal axis is this one. And so all the way around would be 360. My theta prime plus 315 degrees has to equal to 360 degrees. I'm just going to subtract that 315 from both sides. Those will cancel, leaving me with a theta equal to 45 degrees. And that makes sense. 45 and 315 does equal 360. All right, the next one says negative 5 pi over 3. So this one's a little bit different. I start in the standard position, and because theta is negative, I'm going back that direction. And so my reference angle will be that acute angle theta prime with the terminal side and the horizontal axis. In this case, all the way around would be 2 pi. And since I'm going negatively and I want theta prime to be positive, I am just going to go 2 pi minus the 5 pi over 3. And if I change 2 to thirds, I'll have 6 pi over 3. 6 divided by 3 gives me the 2. Subtract away the 5 pi over 3. We'll put our theta prime out in front there. And 6 minus 5 is just 1. So my theta prime is just equal to pi over 3. We wouldn't put 1 pi as our final answer. All right, last example. It says give 2 solutions for the given equation. They want me to give 2 solutions for the cosine of theta equaling to square root of 2 over 2. Now, hopefully, if you're remembering your unit circle, you know that square root of 2 over 2 is on the unit circle. This question asks for 2 solutions. I am here to tell you that there are an infinite amount of solutions. And before I answer this, I just want to show you a method that we've used before to solve problems to show that there are actually an infinite number of solutions. And that method is to set both of these 2 equations equal to y in Desmos and figure out the x values where they intersect. So let's pull up Desmos. All right, so here we are in Desmos, and I've set this up. I've set it up so that the x-axis goes from negative pi over 2 to 6 pi, and that the y-axis goes from negative 2 to positive 2. And in our first row, we're going to go f of x is equal to cosine x. And then in our second row, we'll go g of x is equal to sqrt. That gives me a square root of 2. I'll hit my right arrow, divided by 2. And here we can see that there are already a number of solutions to this problem. And since our first function, f of x equals cosine x, is a periodic function, and g of x is a horizontal line, that is between 0 and 1, we are going to get an infinite number of solutions. I can keep scrolling to the right, and we will see that cosine keeps doing the same thing, and it keeps intersecting. Now, they only want me to find 2 solutions, and I think I can find 2 solutions that are on the unit circle. So let's go back there. I need to figure out, since this is cosine of theta is the x value on the unit circle, and I want it to be positive. So I'll go back up to my unit circle, and I need the x value to be square root of 2 over 2. Well, there is an x value that is square root of 2 over 2, and again, positive square root of 2 over 2. And here is another x value that is positive square root of 2. So the corresponding theta values, theta is usually an angle measure, so I have 2 values for theta, pi over 4 and 7 pi over 4. So I'll come down here and I will say that theta is equal to pi over 4 and 7 pi over 4, and there are infinite number of solutions to this problem, and you can get them by adding multiples of 2 pi to both of these. All right, folks, that's all I got for today. So the Star Wars fun fact of the day: in the original script for A New Hope was focused on General Starkiller, but the story evolved and became more focused on the general's son, Deke Starkiller, whose name was eventually changed to Luke Skywalker. Would have been a lot different if a lead character's name was Deke Starkiller, although still pretty cool. Well, that's all I got for today, folks. Have a great day. Goodbye.